Hello, everyone, and welcome to the 50R1 webinar. Thank you for joining. So we're here live from Bologna in Italy, where we're currently holding various ECMWF events this week, including the Using ECMWF Forecast User event, and the 21st HPC workshop. I'm delighted to introduce our speaker today, Andy Brown. Andy is our Director of Research at ECMWF, and he has led research at ECMWF for the last 8 years. Today, he'll be telling us all about the scientific changes to the IFS in the latest model cycle 50R1. He'll also talk about the model performance. So for those of you in the room, of which there are quite a few, so welcome. If you have any questions, please raise your hand and wait for the roaming microphone. And for those online, please write your questions in the chat. We do have some colleagues online who can answer them, else I will verbally ask Andy at the end. The webinar will be recorded and made available online in the coming days. And with that, I hand over to Andy.
Thank you very much, Becky, and good afternoon to everyone. It's a pleasure to introduce our latest cycle upgrade. For those of us that don't usually come to these webinars, about once a year is our sort of routine of upgrading the ECMWF forecast systems. So this is the next system that we're going to be implementing in the coming months to give you an introduction to what's the main things in it and what you can expect out of it. So our last operational upgrade was back in November 2024 to what we call Cycle 49R1. Since then, we've been working on a cycle which will form the basis of the next reanalyses. We were talking about how powerful the ERA 5 reanalysis has been. There's the ERA 6 reanalysis will be coming next, and a new seasonal forecast system. But here today, I'm going to focus on the next upgrade to the medium range NWP and the sub-seasonal. So that's cycle 50R1. But just before getting into the details of 50R1, just to emphasize that there's an awful lot of changes that benefit our users that happen in between the formal cycles. Is there an echo? So we changed some of the observation usage in between cycles. So for example, in the last year, due to work by our colleagues in KNMI and the UK Met Office, we got access to a lot more aircraft data, global mode S data. There's a new Meteosat, EUMETSAT satellite, the Arctic weather satellite, and so more wave observations. So lots of observational changes have been making your forecast better through the year. But to come back to 50R1, so I'm going to first run at a very high level through all the highlights of 50R1, and then I'll dig into in a little bit more detail into some of the key components. So in terms of science highlights, there's a major package of changes to the ocean. So there's an update to a new ocean model, NEMO 4, and a new sea ice model, the sea ice 3 model. So a completely new ocean and sea ice model. And major changes, which I'll talk about in more detail, to how the assimilation, how we do the ocean assimilation and the atmosphere assimilation in an increasingly coupled sense. So on the waves, there's new work which I'll show in more detail on waves and sea ice interaction. Also changes to the bathymetry for the wave model and the way the wave model fully uses the surface current information. And on the land side, a new glacier parametrization. The current operational system has a very, very crude representation of glaciers where it just effectively assumes it's a very deep layer of snow. Now it's truly representing ice with snow on top of it. Very localized impact, but at very localized points has a major impact on surface temperature. Lots of changes to how we use upper air observations. I can't do any of them justice, but what continues to make ECMWF forecasts keep getting better, sometimes it's single big changes. Very often it's the sum of lots of steps like this. So a new radiative transfer model, we're using humidity assimilation above the tropopause. That was something we did years ago. We took out, we've reintroduced, that sharpens up the tropopause and makes it more realistic. less thinning for some of the satellite data, so using the satellite data at higher resolution and wind tracing. The example I will show on the analysis is using more synop data in the assimilation of 2-meter temperature to improve the near surface temperature forecasts. On the physics side, I'll show results later, changing the vertical diffusion in the stratosphere. That improves the quasi-Bayer oscillation in the stratosphere. And also on the physics in the troposphere, some quite major changes, which I'll show again, which have a long-standing, very reasonable user complaint has been that we very often have convection right on the coast, but the convection fails to penetrate inland. I think we've made some progress in addressing that. And the last slide of general highlights, there's been a lot of work on using single precision and changing our ensemble of data assimilations really to save computational cost. Now that might not sound very exciting. That won't change, that of itself won't change the quality of your forecasts at all. But if you think that we effectively have fixed resource and we can save 40% of our computational cost, a lot of the other exciting things we're doing are enabled by that work. And then the last things I wanted to highlight before I go through a subset in more detail is a couple of changes which are entirely motivated by user feedback and known problems with our operational system. So we introduced a new stochastic physics scheme in the ensemble at the last cycle, and it was very successful. It very significantly improved our forecasts, but we did get some user feedback regarding one specific issue with the 10-meter wind spread. And also, I remember when I gave this webinar a year ago on our last cycle, I was saying cycle 49R1 is great, but it sometimes gives you some stupid-looking tropical cyclones at the start of the forecast. And hopefully I will convince you later that you will no longer have stupid-looking tropical cyclones. So just to run through a subset of these things in more detail. So this is a bit fiddly to explain, but loosely, in our current operational system, when we're doing the data assimilation, so the bringing the observations into the system, it assumes the sea surface temperature and the sea ice concentration is just a fixed boundary condition through that process. So effectively, we're doing the data assimilation in the atmosphere, and the ocean is just a boundary condition. What we're going to here is that each time we do we do multiple loops around the data assimilation, and each time we go around that loop, we're now both doing the atmosphere assimilation and the ocean assimilation. And that means the ocean, ice, and atmosphere observations, there's much more exchange of information across those interfaces to the benefit of both. So just to try to bring that to life in a bit more schematic way. So the satellite is seeing the skin temperature, and it will now give increments to that skin temperature in the atmosphere. 4D variational simulation gets increments in the skin temperature. We then use that skin temperature to constrain the ocean. So the satellite is making our ocean at depth change in this new system. And we can show that by introducing extra atmospheric observations, we're agreeing better with Argo floats at depth in the ocean. We then bring together the ocean observations, the ocean assimilation works, and then it passes that information back to the atmosphere. So there's a sort of a virtuous circle between the atmosphere and the ocean observations, which, we'd all love to have more observations, but huge amounts of money are invested in observations, and this is a way of extracting more so the atmosphere helps the ocean and the ocean helps the atmosphere. Just to give one example, this is the recent tropical cyclone Erin. So this is just the analysis. So this is our estimate of truth. So on the left, we have the operational system, and the contoured colored fields is the model analysis. So that's what we've come up with for the sea surface temperature. And the diamonds are observations of the sea surface temperature. And the thing that really stands out is the three blue diamonds running north-south. So that's the cold wake that Erin caused as it headed north. But because we're effectively fixing the boundary condition, the current operational system doesn't know about that. On the right is what we go to in the sort of the test system of 50R1, and I think you would agree it's much more realistic. So that's just one example of how this more coupled approach to assimilation helps. Changing the subject a bit, at the last site, one of the things our users very reasonably always say they want better is 2-meter temperature forecasts. You know, I'm sure there's lots of users that are interested in some esoteric feature in the stratosphere, but you know, what's the wind going to be near the surface and how much is it going to rain? So in the last cycle, we introduced a simulation of 2-meter temperature observations and got big benefits of that in 2-meter temperature. But we had to do it in a slightly limited way, because if we tried to use a full 12-hour of those observations, the model drifts prevented the system from taking advantage of the new observations. So I'm not going to go into the details, but the DA experts, we've extended the weak constraint version of the assimilation. So it has a sort of an estimate of model error within the data assimilation. And when we put that in, we can now use more temperature observations. And at day one, that gives us another maybe 3% improvements in the surface temperature forecasts. At day 3, perhaps a percent or so. So a worthwhile further improvement to the temperature forecasts. On the model side, so this was the one I alluded to earlier. So we've had numerous comments over the years that if we have convection over the sea, what tends to happen in the system is the convection advects until it hits the coast, and then it stops. And in reality, the convective showers penetrate inland. So there's a couple of examples here. If you look at the top row, so 49R1, the left-hand columns, that's the current operational system. And if you look at the top panel, you see it's very strong, where there's the yellow colours, very strong precipitation right on the west coast of Wales. And if you look at the Latvia and Lithuania example, maybe even more strikingly, you've got this very, very strong band of convection right on the coast and not very much going inland. On both cases, if you look on the right-hand side, what reality was, that there's less on the coast and there's more inland. And the middle column is, in both cases, what the new system would do. And I'm certainly not trying to claim it's perfect, but I think we've both reduced the convection right on the coast and increased the precipitation a bit further inland. So that's effectively being done by handing more information from the model convection scheme into the large-scale cloud scheme, so it can move downstream. I hope that's a significant improvement. It's not the sort of thing you see in globally average scores, but in terms of local utility for the forecasts, I hope that's useful. So I mentioned we've made changes in the stratosphere. You may have heard of the quasi-biennial oscillation, so a periodic oscillation in the upper atmosphere. So the black line is truth here. If you look at the red is effectively where we are with the current operational system. You see there's lots of different forecasts being initialized, but every time the red line sort of tries to pull away from what truth is doing in the black line. And what we've got to is the blue setup, where we've reduced the diffusion and changed one of the gravity wave drag schemes slightly, and it's much better. I think the main significance there is for the more extended range forecasting, when you get to sort of sub-seasonal and particularly seasonal. This mode of variability and the sort of memory in the system aloft is a source of predictability for the longer range forecasts. I've touched on this. I probably won't talk about the details much, but a major upgrade to the sea ice models. So Nemo 4 model. It's now a multi-category sea ice model. In short, it improves the sea surface temperature. It improves the sea ice concentration, which, that's of interest to some users. But again, that helps get a more realistic atmosphere with a better sea surface temperature. And for those that are really aware of the details, we had a rather ugly partial coupling in the extratropics before, that with this improved system, we don't need anymore. Waves, the change here is that the waves are now attenuated by sea ice. What we used to have on the left was if there was less than 30% sea ice, the wave model just ignored the fact there was any sea ice. You know, I'm going to do whatever waves I fancy. And as soon as there was more than 30% of sea ice, the waves stopped. We've now gone to something which sort of attenuates the waves through the sea ice. So effectively, it makes the difference near the ice edges. Clearly, if you're well into the ice, the waves are attenuated to nothing anyway. But for applications in the marginal ice zone, there'll be more realistic wave fields now. And I think this is the two things I mentioned where we've been changing in response to user feedback. As I said, the changes we made at 49R1 are very major changes to stochastic physics, which sort of affects the ensemble spread. And by and large, that was very, very successful, but we did get some feedback both internally and I think from a couple of member state users on a couple of sort of high profile, high wind cases, that the wind above the boundary layer looked reasonably spread, but the wind at 10 meters looked very, very spread. You know, sort of not really credible. Yeah, we can do better than saying we don't know whether it's going to be 20 meters per second or 40 meters per second. So a bit of tuning of just one very specific aspect for the stochastic physics scheme. The panels here are just showing the range between the windiest and the least windy ensemble member. And on the left, you have the 49R1 settings, the current operational settings that we think are a bit excessive, and that's just turned down a bit. And the other example, I mentioned the ensemble initial conditions. In the last cycle, we changed the resolution of our ensemble of data assimilations. And the result of that was the way we construct the initial conditions for the ensemble. If you look at the left two, the top two panels, it didn't happen all the time, but in some ensemble members, you could get some very strange structures. So in that top row, those are meant to be tropical cyclones, which aren't famously double-centered or strange shapes like that. And by introducing a scale-dependent recentering, so how we bring together the mean state and the ensemble of data assimilation, for those same two members, we get to those panels on the bottom. So I think it's largely cosmetic, because by the time you got a day or a few days into the forecast, everything had sorted itself out anyway. But I think in terms of more realistic looking initial conditions for the forecast, it's much better. So that's the sort of the building blocks of the cycle. So does it work? Does it do better forecasts? So apologies for those that aren't used to these scorecards. That's trying to compress far too much information into one slide. But to take it in turn, the left half of the plot is the ensemble control forecast. So comparing 430 forecasts and assimilation cycles with the new system to the old system. The top half of it is verifying against its own analysis. The bottom half is verifying against observations. The different columns are different parts of the world and different forecast ranges. And then the short version is blue is good, red is bad. And I think you'd agree that it's sort of, not entirely, but pretty largely blue. The right panel is effectively the same type of thing, but looking at the ensemble forecast. So probabilistic measures of, is our ensemble forecast better? I think if we're honest, it's not quite as blue as the control forecast, but I hope and think you'd agree it's still, the blues significantly outweigh the reds. And I'll just give a couple of examples now, drawing out some sort of key differences out. So first of all, definitely on the positive side, I do one of these webinars every year, and about the last 4 of them, I've told you a story that this is good in nearly all respects, except we've made the tropics worse. Fortunately, we've made the tropics better this time. So this is looking at the errors in tropical 850 winds on the top and 50 hectopascal winds on the bottom. So blue is the current operational system, red is the new system, and these are errors where down is better. So we're getting improvements in 5, 6, 8%. So the tropical performance is generally, quite strongly of that busy scorecard. I'd say one of the highlights is the tropical performance is better. If we look at cloud and dew point temperature, that's quite strongly better. This isn't the tropics anymore. This is looking in the northern hemisphere. It's also better in the tropics. So I think in general, fairly widespread across the globe. Total cloud cover improves by maybe 7% in the tropics, a couple of percent in the northern hemisphere, and dew point temperature is a lot better in the northern hemisphere. In terms of, now I've got to air the dirty linen, the not quite so positive story. We do have some degradations to the ensemble score for total precipitation and for 10-meter wind. If I show the version which accounts for observation uncertainty, which I think is the fairer way to do it, so the precipitation scores are maybe 2% worse. The ensemble wind score is probably 1% worse. In a sense, that ensemble wind score is a one-to-one consequence of sorting out the overspread by stormed error. So in a sense, I guess we're consciously thinking, based on the user feedback, that having a realistic spread on those cases is more important than optimizing this metric. And on the precipitation, it's a slightly interesting quirk, is so the ensemble precipitation is very slightly degraded. The control forecast precipitation shown in the bottom is actually improved by about the same amount. But certainly more to look at on precipitation, a slightly mixed story, good on the control forecast, less good on the ensemble. So in terms of tropical cyclones, we always do a specific verification, such a key forecast product. I mean, I think the headline of the headlines is it doesn't make that much difference, but in as much as it does make a difference, it's making a good difference. So this is looking just again at the control forecast first. So the plot on the left is the track errors, so the position errors. So the current operational system in blue, the test system in red. So obviously down is good, smaller track errors. I mean, it's within the statistical uncertainty. If you wanted to be optimistic, it's down a bit, and particularly in the sort of the earlier parts of the medium range, there is a small statistically significant improvement. The plots on the right are core pressure errors and maximum wind errors, the mean error and the mean absolute error. Again, not big changes, in as much as there is a change, a hint that it's moving in the right direction. And if I look at the ensemble, in a sense, the story is very similar. The tracks in the ensemble, very, very neutral, I would say. If you look at the core pressure errors and the wind errors on the mean absolute error, a slight improvement. So I wouldn't try and claim dramatic changes, but yeah, a small change in the right direction. So that's all been on the NWP. I was going to finish by just showing, of course, as well as the NWP, to the medium range NWP, we run CAMS, the composition system, as part of the Copernicus work we do for the EU. And when we upgrade the NWP system, there's the other version which inherits the NWP science and makes additional changes to improve the representation for better air quality. So there's the suite we run for aerosols and reactive gases. So not sure I'm going to read these all out, but I will show examples of two of the changes where we've made changes to the emissions data set and to how we treat ozone deposition. And there's a separate greenhouse gas suite where we're getting good value out of the new Copernicus Sentinel 5P satellite assimilation there. So just to show you a couple of examples, one of the big challenges in global air quality forecasting is air quality forecasts are very sensitive to the I can't say anthropogenic emissions that we have to prescribe or use data sets for. And there are big uncertainties and global variations in how accurate those inventories are. Up to now, we've just been using a single global data set. What some of the CAMS contractors did was, if you like, created a mosaic data set, which used the global data set where that was the best thing we had, but brought in places like Europe and China and North America, where we did have better regional data sets. They made a sort of a combined data set, taking the best of all. So, I mean, just to give an example on the bottom right there, that's looking at the bias in near surface sulfur dioxide in North America. And when we were using this sort of global compromised data set, we had quite a significant sulfur dioxide bias. That's the 49R1 line. Maybe unsurprisingly, when you use a more accurate data over North America that we have into the system, that improves. And similarly for ozone dry deposition, we've had user feedback for quite a long time. We have had particularly a wintertime and nighttime bias for surface ozone. We've changed the parameterization effectively of how ozone gets sort of deposited to the ground. So that tends to result in reductions in surface ozone values. And if you look, the bottom right panel again is over North America versus observations. And at 49R1, you see we've got quite significant overestimate of ozone, and that's improved. So I think the composition system is improving both through inheriting the meteorological changes that it gets from the NWP system, and then these specific changes to improve the representation and composition. Then finally on the sub-seasonal forecast. So when we update the medium range forecast, we also update the sub-seasonal, so the forecast going out to six weeks. This is an incredibly busy slide, which I apologise, but just to talk you around it. The left bit is looking at the sort of the weekly anomalies. How good are we at predicting? Is this going to be a warm week or a cold week or a windy week? So weeks 1 to 4 in the different columns. I mean, the short version is it's that those weekly anomalies are a lot better near the surface, and that's really from the better ocean, and in the stratosphere, that's from those physics changes I was talking around. And large, maybe positive if you're feeling optimistic, but certainly not worse than neutral elsewhere. The Madden-Julian oscillations are the major mode of variability in the tropics. It's a major source of predictability. This is looking at the standard MJO index. So blue is good, and so there are small but significant improvements to the predictions of the MJO out for a couple of weeks or more, and the strength of the MJO is increased a bit, which is also a good thing. If we try and look at sort of Euro-Atlantic regimes, blocking, NAO, the rest of it, honestly, I would struggle to say much impact. There's some pluses or some minuses, whether any of it's statistically reliable. So I don't think much change there. So overall, not dramatic changes, but again, changes in the right direction. So I think that's all I've got. I hope I've convinced you. I think there's some very exciting new science in this cycle, and some of which I think is enabler of further improvements, particularly some of this coupled assimilation. We've had a vision for years of looking to extract more out of satellite data, and part of the challenge has been this rather partitioned way of using observations. So as well as immediately helping, I think it opens the door to where we go next. I think, well, I hope you agree that overall the scorecards and tropical cyclone performance are strong. And we've also tried hard with those tropical cyclone initialization, the wind spread, and particularly the convection of precipitation coming inland to address things you don't see in scores, but that are very relevant for many of our users. And I think, I should probably say, probably haven't said when we're going to implement this. So the plan is to implement this in early 2026. So of course we'll make test data available to users, do all the usual communications to give people plenty of time to get used to this. But so the idea here is just to give you an early heads up of what's coming. I think that's me. Do I need to do something?
Try this one. Yeah.
Okay. You showed us a large number of changes in several bits and pieces of the physics and or other bits and pieces of the model. And then, for example, precipitation, practically little effect, but if any negative. Did you, in inverted commas, retune after all those changes? Did you retune the physics you did not change after having introduced all the changes? Because I don't believe very much in linearity of response of bits and pieces of parameterization.
So actually, I mean, the way we construct these cycles is, you have to put things together in a certain order. So we initially go through at lower resolution, the full resolution. So I think we tested some of the data assimilation and observations changes first, and then we had physics changes like the stratosphere diffusion changes that were fairly standalone. And then one of the latest packages was a physics package, which itself was tuned as far as we could against what it was now building on top of. So I think my answer to your question would be, we've tried our best to do exactly what you said. I think the unfortunate reality is that there's so many things we'd like to improve at once. We rarely manage to hit everything at once. And so, yeah, I would rather the ensemble precipitation was very, very blue as well. But I think, across the piece, I think we have an improved system. And of course, where there are aspects we're less keen on, like the tropical cyclone initialization from last time, absolutely, that becomes a priority for our coming work.
Okay, we have one online. What is the schedule release date within Q1 2026, and how far in advance should we anticipate test data being available to users?
You're probably talking to the wrong person here. I think the honest answer in terms of exactly when in Q1, I don't think we have a fixed date yet. We were until quite recently wondering if we could get it in before Christmas, but we were worried that wouldn't give users enough warning and enough time to get ready. So we just recently made the decision we'll go for Q1 and do it properly and get it right. I don't know if Becky or others want to comment more detail.
We can do on the test data. So we do a 3-month release candidate phase. We will be in communication with users when that is available via our normal communication channels. So once we know an actual date, 3 months in advance, we will endeavour to get the data tested out to you. So hopefully that answers your online question.
Or doesn't answer it, but promises to answer it soon.
Thanks. I was interested in the changes in the assimilation and the ocean, and so I think did you check also maybe only coastal station in terms of 2-meter temperature instead of showing the kind of global or all station together in terms of the effects of the changes in the sea?
I suspect we have, but I wouldn't be confident I'm going to know the answer. I can sort of chase up with the experts on that, exactly what's been looked at in that context. I mean, I think we've been quite encouraged. I mean, certainly one of the things out of this system, a combination of the sort of data assimilation and the model, that the Gulf Stream looks a lot better than it has done in previous, including the Gulf Stream separation, which has always been challenging. We always thought we couldn't get that right without going to a higher resolution ocean, whereas it actually looks significantly better at 1/4 degree. That's not quite answering your question, I realise, but I'm happy to get back to the experts, or if any of them are listening, they can write in the chat.
Okay, thanks.
Thank you.
Thank you. I would be interested in this change in the convection, which brought the precipitation going to much more inland than now, because I'm Italian. So yes, in our Met service, we have really very much the problem of the coastline. I wanted to know what has been done. What is the kind of change which has been made?
Okay, so what we're not doing is going to a fully prognostic convection scheme. So it's not, if you like, the convective cells truly going inland. What we're doing is handing over an extra 40% of the convective precipitation into the large-scale cloud scheme, or the large-scale cloud and precipitation scheme. And in a sense, that gives it an advection that there isn't in the convection scheme. So if it's, if you like, warm rain processes, it doesn't tend to get you a very long way inland. So I think we're still underdoing the inland propagation, but it gets a bit further. If it's a sort of a snow case, it actually gets quite a lot further because of the snow falling so slowly. So it's effectively, if you like, an easy way of getting some prognostic memory into the sort of the fall of the precipitation. So a handover of some of the precipitation into the large-scale cloud scheme with a tuning for how much that is, and 40% was the optimum. So I definitely wouldn't try and claim it's the complete answer, but I think, you know, particularly if you live in a coastal or near coastal town or city, I think it makes a big difference.
Any more questions in the room?
Thank you very much for your presentation. I was wondering about this glacier scheme on land.
Yeah.
Does this include now, for example, this calving? I mean, that some big pieces of ice can break and then float into the ocean or something in a coupled atmosphere-ocean model, for example?
No, it's not at that level. It's even in the static sense. It's just how the vertical thermodynamics works. I mean, as you say, the climate Earth system models, obviously the full process, including carving, would be important, but that's not what we're trying to add in here.
Because what I'm asking is that an icon in the coupled atmosphere-ocean model, we have the problem that we are accumulating a lot of snowfall on the glaciers, like in Antarctica and Greenland, and there's not the mechanism to transport all this water back into the ocean. A bit of problem with the global water cycle.
When we have colleagues in the EC Earth community that take the IFS as the sort of the basis of the EC Earth work and make it an Earth system climate model, and of course that sort of issue is relevant there as well.
Exactly.
In an NWP sense, I guess we sort of rely on the assimilation to try and keep us bounded.
We rely on the analysis, I guess. So, of course, snow on glacier is a bit difficult to analyze because of the station measurements missing. Yeah, thanks.
Thank you very much.
A brief question about the seasonal model. You mentioned that it was still coming off of 49R2. I guess two parts. One, will some of the 50 millibar QBO update be ported back to 49R2 to work with that, especially for the subseasonal and seasonal models? And what is just the general timeline of C6 at this point?
So it was a bit complicated to explain. Most of the science I described there is in cycle 49R2, and then 50R1 is getting a few things on top of it. So all of that QBO work, for example, is in 49R2, so absolutely will be in the reanalysis and in C6. So our plan for the next seasonal system, C6, is to hopefully start internally doing the reforecast with it, either at the end of this year or the very start of next year. We'd hope to have sort of test data by quarter two next year. And sort of plan A is that it will run alongside C5 for a few months, but our hope would be in quarter three next year that C6 becomes the new ECMWF operational seasonal system.
Great, thank you. Any last questions? And there are none online. So I will say thank you very much, Andy. Thank you to you all for coming. Have a lovely evening.